Okay, let us discuss this problem. This is related to the moving coil galvanometer. So moving coil galvanometer is a device that can measure the amount of current. So let us discuss first how this galvanometer works. So we are discussing the principle of moving coil galvanometer. So this is about moving coil galvanometer. So what we have, so let us say this diagram. If you see, this is the top view. This is the internal mechanism of moving coil galvanometer, and this is the side view. You have a side view this side. So this is the side view. So this is the side view you have. So if you see from the front, it will look something like this, and this is the internal mechanism how moving coil galvanometer works. So this is the internal mechanism. So this part is more important because I have to know how the moving coil galvanometer works. So if you see, this contains a magnet. This magnet, one part of the magnet this side, and this side another part of the magnet. So one is north, another is south. So let us say this is north and then this is south. So this is two magnets, and these two magnets are basically, it's a semicircular kind of magnet. So these magnets are generally called horse magnets, and these magnets, two horse magnets these are called. These magnets are used to produce radial magnetic field. So you see the magnet, if you see this diagram, so this is the magnet you have here. So this is the north magnet, north pole. This side you have south pole, and the magnetic field lines is something like this. So radial magnetic field lines. Are you getting or not? So here also you have the radial magnetic field lines. Magnetic fields are uniform. So important point. So magnetic fields are radial. So radial magnetic field lines. So you have radial magnetic field lines. That is important. Are you getting or not? And this is uniform. Also it is a uniform magnetic field. So this is also important. So this is again uniform. Now if you see how this works, so if you connect this, and this contains a loop, this is the iron core. So this is made of iron core. So if you see here, this is the same thing as here. So this is the iron core. This is a cylindrical kind of thing, and this contains wire loop. So these are the wire loops. So this loop, this loop. So these are made of a wire. So it's a binding of any kind of wire. You can have iron or you can have copper that can basically conduct the current. And now the lower end of this rod, this is the pivot, this iron core is fixed in a rod, and this lower end of the rod is connected to a spring. So this is a torsional spring. Again on the upper also it connected to a spring. So this means if you try to rotate this iron core, this cylinder kind of thing, so if you try to rotate this side, this will try to oppose. So these two springs will try to oppose, and that's why these springs are called torsional spring. Now if you connect this galvanometer with a current, so there is a current that flows through this loop, and if there is a current, then there is a torque. So torque wants to move this thing, but this spring tries to oppose the movement. Are you getting on? There is a basically pointer. So this is the pointer you have. So a time comes, so if you apply a current I apply a torque, and if the current I is very high, torque is high, and correspondingly this pointer moves. So if you see this diagram, so this pointer moves in this direction. So if you apply a current, this pointer moves in this direction because of the torque. And now this comes into equilibrium somewhere where you have because this torque is also applied by the spring. So restoring torque is applied by a spring, and this torque is proportional to angle theta. So after some theta, what happens? After some rotation, so this rotated by theta angle, after that point, what you will have? You will have the k theta, that is the spring restoring force, is equals to torque applied by the current. So at equilibrium what we have? So this is the one important point we have. So we have at equilibrium, so if you see at equilibrium you have torque by the current, so this is torque by current, is equals to the restoring torque by the spring. So this is restoring torque, restoring by the spring. Now if you remember, a torque on a loop by the current is given as mu cross B. So torque is given by mu cross B. So torque on a loop is given by mu cross B. Let us say we have n number of terms. So mu is NIA. So NIA cross B. So this is the torque by the current. Now another important point, whenever you have equilibrium, your magnetic field lines is this. So this is magnetic field lines and this is your loop. So at equilibrium, so when this torque, both torques are equal, magnetic field lines are always parallel to the loop. This means current in the loop and magnetic field lines always makes 90-degree angle. This is one important point. You see, magnetic field lines are radial. So this is the magnetic field lines. This is the radial magnetic field lines you have. Are you getting? And the direction of loop is again here. So you see here. So this is the loop. So you can see here. So this is the direction of loop. This means area vector is perpendicular. So area vector and B are perpendicular when this comes to the rest. So at the point of equilibrium, I can say A and B are perpendicular. So A is perpendicular to B at equilibrium. So this is another important point. So at equilibrium we will have these two things are perpendicular. So A cross B can be simply written as A into B because sin 90 is 1. So this is NIA B. Now torque due to a spring is basically proportional to theta. So I can write K into theta, where K is torsional constant of a spring. So this is torsional constant of a spring. So now you see, a spring is not simply linear spring. If you have a linear spring that try to restore or that try to resist the expansion or elongation or compression, but this a spring that is a torsional spring try to resist the rotation, and that's why there is a constant K. You have constant K. So if you know the K, basically you can calculate theta. Are you getting or not? Or if you know all this value, you can calculate K. So this is the equation for moving coil galvanometer. That is N into I into A into B is equals to K into theta, where K is the spring constant, torsional spring constant, and the theta is the angle at equilibrium. Are you getting or not? Now let us discuss this problem. So this problem says, in a moving coil galvanometer, torque on the coil can be expressed into torque into K into I, whereas I is through the wire, K is a constant, and the rectangular coil of the galvanometer having number of turns N and moment of inertia I. Find the K. So we have to find, and this is placed in the magnetic field, we find the K in terms of NIAB. Are you getting or not? So we have to find what is the value of K. So you see, T is given as K into I, and T is writing torque. So torque is given as K into I. So now we have to simply equate. So torque is given as K into I. And you see, we have already said torque on loop is given as mu cross B, that is NIAB. So torque is nothing but NAB into I. So this means, this implies I should have K is equals to NAB. So this constant is NAB. So this is your first part of the question. So this is easy. Now let us discuss the next part. So next part says, if the torsional constant of the spring, so we have to find torsional constant of the spring. If the current I naught produces a deflection P by 2, this is not P by 2, this is pi by 2. So this is, deflection is pi by 2. So this is pi. So it produces a deflection of pi by 2 in the coil reaching the equilibrium position. So now I know the theta. So theta is pi by 2. Are you getting or not? So what is happening? Theta is pi by 2. And when the current is I naught. So when I is equals to I naught, theta is pi by 2. Are you getting or not? You see what this question says. So let us read again. So torsional constant, we have to find K, torsional constant. If the current I naught produces deflection pi by 2. So I know if I give current I naught through these wires, these windings, if I give current I naught, this pointer deflects by 90 degrees. This means this pointer is here, and after giving current I naught, this deflects by A current. So this is basically calibration of this galvanometer. So if I know the current, I can calculate what is the constant K. So that is a calibration. Initially we have to make calibration. Any instrument, if I know, I can calibrate. So now I know. So this equation, I have N, I have A, I have B, and I is this time I naught. So let us plug this value I naught, and this becomes K into theta, and theta this time is pi by 2. So from here I can calculate K. So what is K? K is nothing but 2 NAB I naught divided by pi. So this is your K, torsional constant. Now I can use this torsional constant to measure the current, because this is the first stage calibration. So this is what we are doing. We are calibrating the torsional constant. So this is a calibration. So this is nothing but calibration. Now let us say what we have to find in the next part. This also says find the maximum angle through which the coil will deflect if a charge Q. So this is if. So this if charge Q is passed through the coil almost instantaneously. So we have to find what will be the maximum angle through which it can deflect. So maximum angle of deflection. So we have to find maximum angle of deflection. So that is theta max. So let us discuss how we will find. So I have a coil, and through this coil there is a charge that is passing. So through this coil a charge Q is passed, capital Q, and this is for very small time. So now very small time this charge has passed, then there is a torque. So there is a current. So if Q is there, then there is a current, and if there is a current there is a torque. Now if there is a torque, this means this loop will gain an angular velocity omega. So this means I have to have angular velocity omega. So if somehow I can calculate omega, things are easy, because finally if I know the initial omega, so it will have a kinetic energy half pi omega square, and this will be finally converted into total potential energy of a spring. So let us try to see what will happen. You will have something like this. So initially this coil will gain an angular velocity omega, and this will try to move in this direction. It will try to move. So if this moves, a spring becomes compressed. So this will move up till the point when the spring has again this total kinetic energy as a form of potential energy. So at the point of maximum deflection, I will have this the initial potential energy, initial kinetic energy, and this will has to be converted into final potential energy, that is half K theta square, that is theta max solar square. Now only thing is we have to find omega. So how can calculate the omega? Now we know there is a torque. So there is a equation dl by dt is equals to torque external. So if I apply this torque external, we can calculate. So dl by dt is equals to torque external, and torque external is N into I into A into B. So this means I can calculate dl. So dl is nothing but NABI into dt. Now if I integrate both sides, so this becomes change in delta L, change in angular momentum, is equals to NAB, and I into dt is nothing but Q, that is total charge flown through the circuit, and delta L is nothing but I into change in angular momentum is equals to change in I omega, because initial, so this is I into final omega. minus I into initial omega is 0. So this is NABQ. So this means I will have omega is equals to NABQ, this divided by I. So now you have to equate this equation, half I omega square is equals to half K theta max square. So half I omega square, and omega is this, NAB theta BQ divided by I is the moment of inertia. So this I is moment of inertia. Are you getting or not? So half I omega square is equals to half K, and K value I have already calculated in the part 1. So you see K is what? 2 NAB I naught by pi. 2 NAB. So you have here 2 NAB I naught, this divided by pi. So this is your K. Are you getting or not? So you check here, 2 NAB I naught divided by pi. So this is half K and theta max whole square. So from here I can calculate theta max. So this 2 goes, and here you will have, so I also goes. So you can calculate from here. So this I you can calculate yourself. So theta max, so I can write, so this will be, so this side I will have this I goes, so I will have only one I, and this is NABQ, NAB, so this is one NAB will go, so we will have only one NAB. Are you getting or not? So we will have only one NAB, and this is Q, so you will have Q square, and if you take the root of Q, so this will come outside, so you will have NAB, and then divided by I, so this I goes, so you will have AI inside. So this is the moment of inertia I, and this I naught will also come this side, so this I naught will come this side in the denominator, so you will have I into I naught, and this 2, whatever this 2, so this 2 will go in the denominator, so you will have 2 here. What about pi? So this pi will go into the numerator. So this is your maximum theta, Q into NAB pi 2I naught. So you can check the answer again. So you have the same thing here, NAB pi divided by 2I naught. So this is one is I naught. So this is written as simply 2 into I naught. No confusion. NAB pi. So you see NAB pi divided by 2I naught into Q. So this is the maximum deflection you will have.